Welcome back to Genus-X, a podcast where we uncover the hidden layers of technology and innovation. If you've been following along, you know we've been diving deep into the architecture of IoT, the invisible framework shaping the connected world. Last time we unraveled the intricate webs of 1M to M and IoT WF architectures, revealing how they power the devices we use daily. But today we are peeling back another layer. What if I told you there's a simpler yet equally powerful way to understand IoT? A framework so fundamental. It forms the backbone of nearly every IoT system out there. Curious? Let's step into the world of IoT's core architecture where simplicity meets sophistication. So, we're going to see about simplified IoT architecture. So, at the heart of this framework, there are two parallel stacks. One is going to be core IoT function stack, and the other is IoT data management and compute stack. So, this is where it gets fascinating. So, most of the IoT models you'll come across share common core layer, things, a communication network, and application. But this framework takes a bold, innovative approach. It separates core IoT functions and data management into parallel aligned stacks. Why? To give you a sharper, more detailed view of how each layer operates within a complex IoT system. This framework might seem simple on the surface. Beneath lies an intricate system, one that's designed to handle complexities of IoT with elegance and efficiency. At the heart of core IoT functional stack lies three interconnected layers, just like all the other architectures we have seen till now. So at the top, we are going to have the application layer where data comes to life, processed, analyzed, and transformed into actionable insights. Beneath it is the communication and network layer. So this is where the data is ensured to flow seamlessly. And at the foundation sits the things layer. So this is where the sensors and actuators are going to collect the data, and they're going to act as the eyes, ears, and hands of our IoT system. But that's just one side of the equation. We have the IoT data management and compute stack. This brings another dimension to our IoT system. Here, the action is spread across three levels. The cloud layer, so this is where massive data crunching and long-term data storage is going to take place. And then we are going to have the fog layer, where gateways act as intermediaries, managing data closer to its source. And finally, the edge layer, where raw data collection begins right at the sensor level. Let's zoom in on the things layer, where the physical world meets the digital. At this layer, devices like the sensors and actuators must adapt to their environments while still delivering the data we need. But what makes these things truly fascinating is how diverse and versatile they can be. First, there's the question of power. Are these devices battery powered or power connected? So, if suppose they are battery powered devices, they offer mobility, but they are constrained by energy limits, impacting how far they can transmit the signals and how often they can report. On the other hand, power connected devices enjoy continuous energy but lose the freedom to move. Next, consider whether a device is a mobile or static. So, some sensors like your location tracker on moving goods must stay dynamic, while others like a moisture sensor embedded in a field remain stationary. This mobility defines not only how they operate but also how they are powered and connected. Another intriguing factor is reporting frequency. So some devices only need to report periodically, like a rush sensor sending updates monthly. Others, like the motion sensors, might report hundreds of times per second, demanding more power and precision. Then there's the richness of data itself, simple or rich. Imagine a field humidity sensor sending a simple binary value daily versus an engine sensor reporting intricate parameters like temperature, pressure, and gas velocity. Richer data demands more power, bandwidth, and sometimes patience. Let's not forget the reporting range. While your fitness band only needs to communicate a few meters to your phone, a moisture sensor embedded in a road might need to reach its gateway hundreds of meters or even kilometers away. Lastly, the object density per cell. So in some cases like oil pipelines, a single sensor every few miles might suffice. But in scenarios like the SETI Colossus telescope, where thousands of mirrors operate in a confined space, the density of sensors is astounding. Together, these classifications create a vivid picture of the things layer, dynamic, adaptable, and vital to the IoT ecosystem. And the beauty? Everything has a story to tell, a role to play, and a challenge to overcome in this interconnected world. Let's shift our focus to the communication network layer. So, the bridge that connects the IoT smart objects to the digital world. So, when these objects are in self contained, they rely on this layer to communicate with the external system, often through wireless communication. So now when we're seeing about the communication network layer, there are sub layers that we have to look into precisely. So the first is the access network layer. So this is also called as the last mile, meaning this is what it takes for an object to connect to the network that is out there. It might be a Wi-Fi, it might be a Bluetooth. So this is the last mile that the data must take from the object, tell the sensors, to the network. So these could be technologies like 802.11ah, 802.154g, and LoRa. They form crucial links between sensors and the network. So whether they are wired or wireless, this sublayer ensures every device has a voice, meaning every device can connect to the network. So now I just said 802.11ah, 802.154g. So what are they? They are all protocols. So 802.11ah is a low power wide range protocol, and then IEEE 80154 is a low cost, low data rate wireless access technology for devices that are operated or work on batteries. And then you have LoRa, which is long range Wi-Fi access technology. So these are all the access technologies that are used these days, and the use might differ based on what kind of internet protocol version you're using. It's IPv6 or IPv4. So we'll be looking into it later on as into what they are. Next is the gateways and backhaul network sublayer. Picture this, a cluster of smart devices reporting to a single unified gateway. This gateway acts like a digital post office, forwarding collected data over long distances, what we call the backhaul, to a central processing station. But that's not all. Gateways also handle layer 7 application functions and can even act as routers in IP networks. Then we have the network transport sublayer. It is the unsung hero that ensures successful communication by implementing protocols like IP and UDP. Without it, the diverse IoT ecosystem could not connect or operate cohesively. Now, moving on to the application and the analytics layer. In the world of IoT, there are two main types of application: analytics and control. So, the analytics application collects and processes data from multiple smart objects, offering insights that a single object alone cannot provide. So, these applications help visualize trends, historical data, and system statuses. As in, like the control application, adjusts the behavior of smart objects or connected devices based on the collected data. For example, if a pressure sensor detects low pressure, the system might automatically increase the speed of the connected pump. Then we have the analytics, can also be split into two types: data analytics and network analytics. Data analytics process data from sensors, turning it into meaningful information like predicting a storm based on multiple sensor readings or detecting when a robot might need servicing. Network analytics focuses on monitoring the system's network connectivity, which is crucial for IoT system to function efficiently. So now these are the three layers which are present in the core stack of the simplified IoT architecture. Now suppose we are going into the IoT data management and compute stack. There are three layers in it: the cloud, which is parallel to the application layer. Then we have the fog, which is parallel to the communication network layer. And then we have the edge, which is parallel to the things and sensor layer. So the fog and the edge layer work on something called the distributive computer paradigm, meaning that they distribute the work to many computers. So what we are doing here is that when the sensor collects the data, there will be a processing or analysis, choosing whether that data is necessary or not, or any other low level processing that has to be done could be done at this particular layer, which is called the edge computing layer. And then the next is the fog computing layer, which provides us geographical distribution, and because of that you'll have low latency. Then we have the cloud computing layer. So this is actually an on-demand computer service, and you don't have to set up your infrastructure or something like that. There are services provided by many industries. They provide storage, processing, and application. You just have to pay a particular rent for it. There are 3 services that they could provide. One is IaaS, then you have SaaS, and then you have PaaS. So IaaS is infrastructure as a service. So you could actually rent a virtual hardware for storage and processing power and networking without actually setting up your own hardwares for storage and processing on your own. Then you have SaaS, which is actually software as a service, which delivers software through internet for various software needs. Then you have PaaS, which is platform as a service. So if you need a development platform, this service is very useful because they provide a development platform to develop and test applications. Now we saw a lot of internet protocols, the networking protocols. So the main, if suppose you want to really understand what those protocols is, that we have something called the OSI model. This we are going to see the OSI model layers, because we saw how for accessing network you use the protocol, and then for transmitting the data you use the protocol, and then to receive a particular data for a particular smart device there is a protocol. So OSI model layer depicts what are these layers are. So the full form of OSI is Open System Interconnection. There are a variety of layers in it, like the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, application layer. But we are going to see mainly 3 layers. First is the application layer. So its purpose is that it provides interface and services for the user to interact with the network. One known protocol is HTTP, which is also known as Hypertext Transfer Protocol, which is used for web browsing and used with World Wide Web. And then you have TLS, which is Transport Layer Security, which ensures secure communication over internet by encrypting data. Then you have DNS, which is Domain Name System, which translates the domain's name, like for example www.google.com into an IP address. Then we have something called the transport layer. So its purpose is to handle end-to-end communication between devices, ensuring reliable data delivery or fast transfer depending on the protocol. So the most used protocols are TCP and UDP. TCP is Transmission Control Protocol. So it ensures reliable, ordered and error-checked delivery of data. So this is usually used for downloading files. And then you have UDP, which is User Datagram Protocol. It's a faster, connectionless protocol used where speed is more critical than reliability. Example, live video streaming. We have the network layer, which is responsible for routing data between devices on different networks by using IP addresses. So the internet protocol includes IPv4 and IPv6. It determines the best path for data to travel to reach its destination. Then we have the link layer. So its purpose is to manage the physical connection between devices in the same network. This includes how data is formatted and transmitted over physical media. Example, Ethernet, a wired technology for local area networks, and then you have wireless LAN, so which is wireless technology for connecting devices. So thank you for watching. This is Kiara Knight signing off. See you in the next episode.